Hello again to everybody that's just joining. We'll start in a couple of minutes when we've given a chance for everybody to connect that wants to. Okay, I think the number of attendees has stabilized a bit now, so I think we can begin. Welcome everybody to this.
Recording in progress.
Yes, thank you. Yeah, so welcome everybody to this latest edition of the FHI AIMS webinar series. And the subject of this webinar is Explainable AI Models for Materials Science with the SISSO approach. And we have two talks today. The first will be given by Thomas Purcell on an introduction to SISSO and recent advances in the methodology. Tom got his bachelor's degree in chemistry from New York University, and then got in 2018 his PhD in physical chemistry at Northwestern University. Following this, he was an Alexander von Humboldt Fellow and then subsequently a group leader here at the NOMAD Lab at the Fritz Haber Institute in Berlin. And since January 2024, he's been an assistant professor at the University of Arizona. His research involves creating AI-guided workflows for materials discovery, in particular in low data regimes. And you'll hear in his talk about how SISSO is particularly good for this. As the time right now is quite early in Arizona, his talk is pre-recorded and will be played shortly. However, he will be here for questions after his talk. The second talk will be by Lucas Vopper on describing materials properties and functions via the materials genes concept. He got his bachelor's in chemical engineering and master's in chemistry from the Federal University of Rio Grande do Sul in Porto Alegre in Brazil, and then his PhD at ETH Zurich in 2018. Since then, he was first a postdoc at the NOMAD Lab and subsequently now a group leader here at the Fritz Haber Institute in Berlin. and his research is focused on the integration of experimental and theoretical approaches in material science and heterogeneous catalysis via AI, and on the development of AI methodologies based on symbolic regression and subgroup discovery. So as well as these two talks, we actually have a second day in this webinar, which is a hands-on session, which will be tomorrow. So we actually have two time slots for this, one in the morning in European time and one in the afternoon in European time. Both of these will be exactly the same session, just to accommodate different time zones. People who have signed up should have a few hours ago received an email on how to access the tutorial tomorrow, as well as a link to a Slack channel, which you can join if you have any questions or discussion items tomorrow. And yeah, anybody who is welcome to join as well. So if you haven't already signed up, you're still able to do so, or you can also just join via the Zoom link tomorrow. The topic of the hands-on session tomorrow will be using a user-friendly web application for active learning-based materials exploration. So this web application involves SISSO, which you'll hear about today, and active learning in a workflow format to explore material spaces. This SISSO and active learning web application is also interfaced with FHI aims, although tomorrow there won't actually be FHI aims calculations. We'll be using pre-calculated data to speed up the tutorial, and also so the main focus can be on using this web application and how the SISSO and active learning methods are integrated into this. And so yes, with that, I think we can begin with Tom's talk. So I will let Konstantin share Tom's talk.
Hello, my name is Thomas Purcell. I'm currently an assistant professor at the University of Arizona in the Chemistry and Biochemistry departments, and was formerly a postdoctoral fellow-group leader at the Fritz Haber Institute in the Nomad Laboratory. And today, I'll be introducing you to the SISSO methodology and some recent advances that I made in it while at the FHI and here in Arizona. However, I want to briefly apologize for not being able to attend this session live via Zoom because the time zone difference between Arizona and Europe made it fairly impractical for me to give this talk live. However, after Lucas's talk, I should be able to join the call for Q&A and would be happy to answer any questions of the SISSO methodology then. Before addressing SISSO itself, I want to first briefly discuss the class of methodologies that SISSO is a part of, mainly symbolic regression. Symbolic regression is a way of approximating a target property for some system as a function f of some set of inputs, here shown as x and y, as an analytical function. For example, sine of 2.3 times x times y plus pi over 4. The reason why this method is becoming increasingly popular in the sciences is that in the model accuracy and interpretability Pareto front, it's normally viewed to be in between decision trees and linear logistic regression, meaning that we can get fairly accurate models that has physical insights in it that we can fairly readily interpret. And on computers, how we actually store the underlying expression symbolic regression found is normally through these binary expression trees. And the reason for this is twofold. One, it is a unique mapping onto an analytical expression without having to worry about parentheses, brackets, or any of that. And two, we can define anything about a given expression by simply doing a proper transit of the trees themselves. And this will actually lead us directly to a stack that we can convert these trees into a set of computational instructions in order to calculate the final property estimates. And how we can think about this is that we have access to different levels of complexity, by thinking about the trees themselves in terms of both the height, which is represented by rung in SISSO, and our primary way of describing the complexity. So this basically is called a rung because we think of it as a rung of a ladder. As we go up and increase more and more operations on top of these trees, we get more complicated and more descriptive expressions. And we can read these somewhat by saying that all nodes represents either functions if it's not a leaf node or not at the bottom of these trees, and all variables or constants are these leaf nodes here. One can think of variables or as constants as a variable, which is a constant value set to whatever the name of that variable is. We can think of the edges of these trees as function compositions. So for example, if we define g of x of y to be this multiplication operator, once we add this sign of x on top of it and declare that to be f of x, then this underlying expression is essentially f of g of x of y. And we can define this overall as h and x and y. Importantly, it also allows us to define things such as values, expressions, units, and ranges recursively by going down these trees. What makes SISSO fairly unique in the symbolic regression landscape is that it's a deterministic way of finding these expressions. How it does this is that it uses a feature creation step in order to generate a library of billions or trillions of candidate descriptors, and then uses compressed sensing to find the best 1, 2, or 3 of these candidate descriptors to describe some target property. This is why we typically call SISSO to be a combination of symbolic regression and compressed sensing, where the final vector and model that we get is essentially a set of these candidate descriptors merged together in some type of linear model. And the first step of SISSO is always going to be to build up our library of candidate descriptors. For this, a user only has to define a set of operators, here shown as the sign of x and multiplication as blue and green respectively, and some set of primary features or leaf nodes on these trees, here shown as a time feature in orange and a frequency feature in purple. We then start applying the operators onto the primary features and previously generated features recursively, following some physical law. So for example, for rung 1, there's only one valid candidate descriptor that can be generated from this, mainly the multiplication of this time and frequency term. This is because both of these are united quantities, and taking the sign of a united quantity doesn't make physical sense. Well, we can do it mathematically. Nobody has defined what the sign of a second is, so therefore you can't really do it in a physical mindset. However, once you multiply these two features together, the unit cancels out. So for rung 2, we can actually start to take the sign of it, as well as continue on these multiplication trees here, where essentially we've taken this rung 1 feature and multiplied on the two primary features. And this can continue for as long as possible until we realistically hit a computational limit of how many of these trees we can store on a computer, or how many trees we can feasibly scan through in a reasonable amount of time. In SISSO, we always define and reference these features as the root node of our binary expression trees, here shown in this thicker border. And the height of the root node essentially corresponds directly to rung. So rung 0 always corresponds to primary features only. And then essentially rung 1 and 2 is one level up, or 2 levels up from this primary feature. As well as by addressing these root nodes directly, we can define everything from the candidate descriptor as a recursive function defined from this operation here, and properties passed from the user in its initial data collection phase for the expressions, the unit, the range, and the values, where these three terms here shown in the node are all things defined in our column header of our data file. The reason why this is important is we can now keep track of a lot of physically relevant information, and that provides us ways of adding on grammatical rules for symbolic regression. The first one that we actually implemented was known as units, and making sure that the candidate descriptors themselves are physically meaningful terms. What I mean here is that if you have some dimension to object or property A and some dimension to property B, physically they must follow some rules in order to be combined. Here we can actually keep track of that by first defining different units for different operators by combining them in this way. So a unit is essentially a multiplicative algebra system. So that means that for addition and subtraction, the unit of A plus B will simply be the unit of A, and the unit of A times B or A divided by B would essentially just be the unit of A times B and unit of A divided by the unit of B. For transcendental operators, we always set this to be a unitless quantity because, again, you can't really define the unit of the cosine of something. It doesn't take on units. It doesn't fit within the algebra itself. And polynomial terms are just treated as if they were multiplication or division. And we do this because we want to create restrictions on what different types of candidate descriptors are allowable. So for example, I mentioned previously that the unit of A plus the unit of B is equal to the unit of A. This is because in the code we restrict it such that the unit of A and unit of B must be exactly the same in order for it to be applied in addition. And you can think of this as you can't really take something with dimensions of distance and add it to something with dimensions of time. However, it's important to note that SISSO doesn't really understand length and times, but thinks of the unit as its own dimension, so it wouldn't really be able to add a meter with an inch, for example. An additional restriction is that all transcendental operators must only act on unitless quantities. This is just to make sure that they're physically meaningful and physically make some sense. And importantly, as you noted, might have saw in a previous slide, we're also including the range of our various features. The reason why we're doing this is because there are cases where our training data might not necessarily contain any problematic values, but in the range of possible values encompassed by that descriptor or that primary feature, problems can arise. So this is a very simple example where we're trying to find a model for y that is simply 1 over the absolute value of x. And to do this, we're training on all the large values in terms of magnitude of x, where x naught goes from a range of -5 to 5.0 and is defined as x plus some Gaussian noise term with a standard deviation of 0.025. By doing this and looking at the test set, we see that there's some very large errors here. This is because we can get very small values of x. This 0.025 Gaussian noise term can then be quite significant. And by dividing it, by doing 1 over that value, we're then further amplifying this problem, meaning that this, while the training data looks great, there's fairly massive problems on the test data set. This can even go up to nans, for example, if we have logarithms or square roots. So we allow the user to potentially define the theoretical range of a given primary feature and keep track of what the range should be by applying different algebraic terms on it. So for example, if you have a sine, the range will automatically go from -1 to 1. If you take a square root, we can define the square root of the min and the square root of the max as the possible range. For the operators, those are just examples. I'm not going to go through the entire table with you. That's in this paper here in JPhysChem. And from this, we can now say that, okay, even though this feature here, x1, which has a larger Gaussian noise term of the training data, isn't as good, we know that the range of this particular input, 0.125 to 5, is within the domain of the previous operation shown here on this slide. So division can't contain 0, logarithms can't contain non-positive values, square roots can't contain negative, and therefore we should reject this particular model x naught in favor of x1, so we can ensure ourselves that we don't have anything very strange or wrong going on. And finally, SISSO++ has one other key advance in SISSO that allows it to address some more fundamental problems in symbolic regression. Mainly, if we think back to how we construct our feature space, there is no internal constants within these operators themselves. It's just t times omega. And then when we take the sign of that, it's just t times omega. It's sine of t times omega. What if there's a phase shift? What if there's some type of frequency shift going on? Well, if we try to pass this into SISSO itself, so this is just a sine function of x and y with some frequency and some phase shift added to it, SISSO doesn't know what to do with it because it can't actually find those expressions. Similarly here with this Lorentzian, moving it slightly off center means that it's no longer accessible for SISSO to find. So in order to get around this, we implemented a nonlinear optimization scheme that we call parametric SISSO in order to find these more complicated expressions. So how this works is that each operator has a possibility of having a scale term alpha and a shift term beta. And we define it such that there is no possibility of linear dependency. So for example, the square term, we only have beta because alpha times x squared plus beta, or x plus beta squared, is essentially the same, or can be mapped onto alpha x squared plus beta. So we don't necessarily include all possible features. We exclude anything where we get linear dependencies on, and then we can store these parameters as a vector on our head node. So here we see that the x plus beta term here is beta sine 1 instead of alpha sine 0 and beta sine 0. So we can think of this as it's a parameter stored on that head node, but is associated with this squaring term. We also allow for a hyperparameter such that we can do this parameterization scheme on the entire tree or on just a head node. So if you do it only on a head node level, that means this x plus beta term is actually using what was ever stored for the nonlinear optimization of the square value here. It makes it slightly easier to do and can, in some cases, actually give you slightly better results because of various noise factors that can be going into it. And if we were to do this on a non-parameterized operator, then at the head level 1, we just completely exclude that type of operation. That's really why we have this hyperparameter, is so we can combine things with non-parameterized features and have that be fixed in stone, essentially. We can then optimize these parameters utilizing a loss function. Here, we're doing a log-based loss function in order to better handle outliers, which is a known problem in these types of situations, and then perform a local optimization using the subplex algorithm, which is a variant of the Nedler-Mead approach, where we essentially have a triangular walker trying to find a global minimum or global maximum on a landscape, shown here in this animation, where the subplex basically splits our space more efficiently to allow us to explore a larger space in a fairly efficient manner. We can then do an optional global optimization in order to make sure that our initial guess isn't locking the structure or locking the parameters into a non-optimal part of the parameter space, before doing a final local optimization using the subplex algorithm again, but with slightly more stringent conditions for convergence. Doing this, we can now actually find both the Lorentzian and sine curves with fairly easy time of it. However, it is a nonlinear optimization, and in theory, these could go on forever. And unfortunately, we don't have that kind of time. So there is some limitations to it, such that if it goes for too long, we just stop it off prematurely, even though they're not converged. This has been defined in this JPhysChem paper here, but it's typically on the order of a few hundred iterations. This means that there are going to be some cases that are just too hard to find, such as this very high frequency sine curve or this very thin Lorentzian. And while the parametric SISSO won't perfectly match it up, we do see some type of peak structure with this methodology, as well as some type of general periodic thing, even though it's not perfect. This allows us to gain some insights through this parameterization scheme that would otherwise not be available. With our now completely generated feature space, we can now actually utilize the SISSO algorithm to find the best low-dimensional descriptor. How this works is that we screen over all all candidate descriptors against the target property utilizing some type of correlation metric, store the most correlated species or candidate descriptors in a subspace known as S1D, and trivially find the best one-dimensional descriptor from that. We can then calculate the residual of these models, screen which input features best map onto these residuals, store those into a subspace known as S2D, and by performing an L0 regularized regression on the union of these two subspaces, we can find the best two-dimensional descriptors, and this goes on until we hit some type of convergence criteria. Historically, SISSO only looked at the top model when doing this procedure. However, this isn't always going to lead to optimal results, as this very simple toy example will show you. This corresponds to a data set with 3 data points, here shown as E1, E2, and E3, essentially setting the unit vectors that spans our feature space, and 5 input features: F1, F2, F3, F4, and F5. Here, we see that the best model is going to be F1, as it has the smallest residual and highest projection score on our target property, here shown as this purple vector P. But F2 does do a fairly good job. However, if we only look at the top residuals shown here on the top, we would see that F4 and F5 are actually the 2 input features or the 2 candidate descriptors most highly correlated to this residual here, so they would be selected, completely missing out on the fact that our F3 one here perfectly aligns with the residual from F2. This means that utilizing this multiple residual approach, we can find the optimal model more quickly than if we were to do a standard one residual approach, as in this very simple toy example that I made to describe this procedure or these happenings more easily, we would need to go to a third dimension. However, this is in fact a hyperparameter that we cannot maximally choose a value and assume that's going to be good. This is because we have to make a choice where this projection score for cis with multiple residuals is going to be the maximum across all of them. So we're not going to take the n-cis candidate descriptors that best map onto each residual for numerical consistency reasons. This means there are going to be cases where, for example, here, if we look at 5 residuals instead of 1, we consistently get worse performing models on 2 dimensions. This can be mitigated by just adding this as a hyperparameter that you need to optimize during hyperparameter optimization, where we see that it does significantly improve the performance of our 2D models utilizing 10 residuals. And this is comparing different cis subspace sizes, or NCIS here. And if we go to three-dimensional cases, we also see consistently better results. Here you might be slightly surprised. By increasing our cis subspace, we can actually have an increase of error in 3D. This is an artifact of the underlying projection procedures that we're doing and utilizing these subspaces. For a two-dimensional model, you always assume monotonically decreasing, or at least constant and decreasing. However, by going into, for example, a drop here, we can actually get slightly different features that pop up within these projection spaces, meaning that you could be missing out something that's important for higher dimensional models. This just means that we always have to assume that the hyperparameters for SISSO must be treated as hyperparameters, not something to just maximally increase the values of in order to just assume that's going to be good. They are, in fact, hyperparameters, and they must be optimized. Finally, we also have a consistent classification algorithm now where we perform an SVM classification procedure in order to make predictions of some type of models for the system. This is just an improvement over the simple convex hull approach that we did in previous classification schemes, where we didn't really have a way of making predictions on new data points. So it's just showing that it works for this 4-class system, where we basically just took a random sphere, cut it via planes, and then did some SVM logic to it in order to create these classes. So it is an important advancement where we now have prediction capabilities for both regression and classification problems. However, there is one very big drawback of symbolic regression, is that it is an NP-hard problem with combinatorial scaling. This is best shown in the feature creation space. However, to have just one operator and two primary features, we see that rung one type of candidate descriptor, no problem. Rung two candidate descriptors, no problem. Rung 3, we now have 1, 2, 3, 4, 5, 6, 7. And rung 4 would just continue this combinatorial train going. As we can see here, for rung 4, if we go beyond 2 or 4 input features, it's real hard to justify the use of it because it's just too complicated to create all these various candidate descriptors. We also see a similar combinatorial problem in the descriptor identification step utilizing the SISSO algorithm related to the L0 regularized regression, where as we go up to fifth dimensional models, we're really restricted to roughly 50 to 100 as our NCIS select size, because otherwise the number of models that we would need to test become too great. So for example, if we were to go up to 1,000, we would essentially need an exascale computer in order just to calculate the fifth dimensional model case. And realistically, this is just impractical to do. However, these combinatorial scaling problems also have the advantage in that it's very easy to port these onto GPUs to restrict our amount of time we take in numerical parts of the code. In fact, if we were to look at a case that we purposefully designed to be the least numerical, so this is from a Kaggle competition data set looking at the energy of formation for various aluminum, indium, gallium, oxide materials. There's 2,400 data points in this data set, and we set an NCIS select size to be 50,000 in order to basically maximize the amount of non-numerical work and communication-related work we would have here in the SIS step, we can get economic performance in this worst case scenario by just simply using a hybrid CPU plus GPU approach with single precision numbers. So we see a 4.71 speed up above the 4 times speed up that you would need to have as an economic break-even point, essentially. And this is a worst case scenario. We do have better results from more realistic systems. I just want to highlight the importance of utilizing modern computational tools to address some of these more fundamental algorithmic problems. And we can see that both feature creation step and L0 step, which are the more numerically heavy terms, are performing quite well. And again, if we're to use a system that has more favorable characteristics, this porting is even better. Importantly, we use Caucus in order to do this, allowing us to have a portability within our porting, so we can not just look at A100 GPUs, which we saw previously, but also AMD GPUs such as MI250s and MI300As. You notice here the MI300A is slightly longer or larger time than the MI250s and A100s. This isn't really a worse GPU performance. It's just that these nodes have slightly fewer GPUs per node than the A100 or MI250 nodes. And throughout all of this porting work, we ensure that the great MPI scaling of SISSO is preserved. So we have near linear scaling on both CPUs and GPUs up until the baseline amount of work that has to be done for all calculations. We do start to see a tail off here, but this is to be expected given various system sizes. If we were to increase the problem slightly, we would expect that the scaling would continue on ad infinitum because this is a fairly trivial scaling problem. With that, if you want to get access to the code, you can find it here in this tiny URL for the Git repository. There's this JCP paper, covers most of the advances that I highlighted in the underlying algorithms. This paper here is simply an implementation paper describing the capabilities of the code and highlighting the fact that this is a very well documented code. And I'll be happy to take any questions after Lucas's talk. I hope you enjoy the rest of the session.
Okay, so thank you to Tom for this talk, and yeah, he is actually here already, so can already take questions, so we don't need to wait until after Lucas's talk. So yeah, if you want to use so for people on Zoom, want to use the Q&A feature to write your questions, or you can raise your hand and we can unmute you so you can speak with your questions. And for people watching on YouTube, you can write in the chat there, and people on Kushare can also write in the chat there, and we'll monitor these things. So yeah, I think we already do have one hand up from Reza, so I just will allow you to talk. And yes, so if you can unmute when you're able and ask your question. I don't know. Yeah, Reza, if you manage to unmute and ask a question at some point, we can come back to you.
So James, can you unmute the person?
I can ask to unmute, but I can't make them unmute. So yeah, yeah, unmuted now. So yeah, Reza, if you want to ask your question, you can go ahead.
If you're trying to speak, Reza, it looks like your hardware muted as well, potentially.
Okay, maybe Reza will come back to you afterwards. Or you can also write in the Q&A your question if you want to ask that. But we have another hand up from Sebastian, so I will just allow you to unmute and allow you to. So yeah, you can unmute Sebastian with your question.
Hi, can you hear me?
Yes, yeah, we can hear
Yes.
you.
Thank you for the presentation. It was really nice. I just have one question. I think I missed the detail. So with SISSO, you generate these descriptors with the functions. And how do you go from these descriptors to the model? How do you use these descriptors and transform it into a model for predictions?
Yes, let me share my screen real fast. Okay, I think my screen is being shared. Yes. That is what this step is doing here,
Okay.
where we generate our candidate descriptor space, and here it's represented for a very trivial problem of 3 data points. So you have 3 vectors here and 5 features with 1 property in this purple vector. We screen all of the possible descriptors and see which ones are most correlated to a given target property. Here it's F1 and F2. We store those into a subspace, in this case S1D, and then we can find the best one-dimensional descriptor by saying which one is most correlated to the target property. We then calculate the residuals. Here they are these delta vectors. See which of the input features are most correlated to a given residual, with the number of residuals being this nres hyperparameter here, so in this case 1 or 2. Store those into a different subspace of S2D, and by performing an L0 regularized regression on the union of the two S1D and S2D descriptor spaces, we can find the best 2-dimensional model, which is essentially just a linear regression model combining these 2 nonlinear features into it. And then this continues until we hit some type of n-dimensional model.
Okay, so the choice of how many levels to go, is it a parameter that we need to decide?
That is a hyperparameter that we normally set through cross-validation. So if we look at this chart, we would see that by going from a 2-dimensional model to a 3-dimensional model, we get a slight performance improvement. Normally, once this hits a plateau, we cut off the calculation, say that's the optimal model to ensure that there's not some type of overfitting going on.
Okay, great. Thank you.
No problem.
Thank you, Sebastian, for your question. Yeah, so we have a question in the Q&A from Vasilios Raptis. So he says, congratulations for the presentation. Is symbolic regression somehow related to the technique of grammatical evolution?
Parts of it are, I think. There are genetic programming bases for symbolic regression, which you can probably reframe as a grammatical evolution problem, but I don't know all of the details of grammatical evolution to be sure the exact one-to-one corollaries and where they differ.
Okay, thank you, Tom, for that answer. I don't see any other questions for the moment. Maybe I can ask a general question then, Tom. So you showed quite a few improvements to SISSO and SISSO++ in this presentation with these toy models or mathematical models to illustrate the improvements. But how from like a practical point of view, do these improvements help materials discovery? Like, do you have examples where it show that these new features help with discovering new materials?
So how it basically helps, for one thing, the GPU optimization helps because it shortens down the amount of time needed to actually solve the model, so you can do this in a more robust manner, essentially. For some of the more methodological improvements, it essentially is trying to introduce more grammatical rules to the feature creation process to ensure that you don't get uh, odd or nonsensical results. So, for example, without this domain range checking feature we're showing here, it would not be uncommon to see a single data point have errors on the order of 10 to the 25 because you just happen to be dividing by 0 or something very close to 0, and that one data point completely screws up your cross-validation check, for example. The parametric SISSO helps by allowing you to explore a more complete feature space, and units were introduced to essentially remove a common criticism of symbolic regression when applying to physical properties, in that you get expressions that, as a physicist, you say this doesn't make sense because they are combining dimensions that shouldn't be combined. They're doing things with exponentials that shouldn't be done. And this just alleviates those things.
Great, thank you. Still no hands up and question in the chat. So yeah, maybe I just ask one other general question. Oh, yeah, one other question then. So you showed this scaling behavior of SISSO when you have higher rungs on your model. So do you ever need to go really beyond rung 3 for practical purposes where you have this kind of bad scaling behavior?
That is difficult to answer because, in practical terms, going beyond rung 3 is almost impossible for modern computing technology and standard feature sizes. So we can get accurate models with rung 3, but answering the question, is there any point to going beyond it? Maybe there's an even better model that extra dimension would unlock and make more physical sense. So it's hard to answer directly in a concrete way, but typically rung 3 will give you fairly reasonable results that are in line with other regressor techniques, which imply that you're at a reasonable level of accuracy for a given data set, if that answers your question.
Yes, perfect. Thanks, Tom. So yeah, we've got one more question, and then I think we'll move on to Lucas's talk. So this is the Q&A by Xiaoyu Wang, and apologies if I pronounced your name incorrectly. So they say, thank you for your report. I've tried to use SISSO, but the formula obtained is very complex and still difficult to understand. I think you mentioned that the unit limit will greatly increase the readability of the formula, which is good. Are there any other suggestions to increase the probability of acquiring readable knowledge?
Yes. So let me see if I have a presentation on this available. I know I do somewhere. That should. Did my screen share change, or is it still on the presentation I gave?
Still on the one you gave, unfortunately.
Okay. let's here. Okay, it should now be changed, correct?
Yes, now it's changed.
So for this model, we still have complicated formulas that are difficult to fully understand. However, you can do post-processing techniques, in this case showing the SHAP and Sobel values to get the most important input features here. And then by sampling the model over a distribution that is mapped onto your input space, you can actually understand what the expected value of your models are given a particular range here, which allows you to gain some of those more physical insights out from it beyond just looking at an analytical expression, because it is difficult for most people to see a 7 or 10 input uh, equation and then understand intuitively what's going on. So that's why we also support these type of post-processing techniques where we can better visualize what's going on.
Okay, then yeah, thank you. Hopefully that answered your question. And yeah, thank you, Tom, again for the talk and for being here very early in the morning in Arizona to answer the question. So yeah, and now I think we can move on to Lucas's talk as well. Thank you again, Tom.
Thank you.
Okay, so I just unmuted myself. I hope everything is fine.
Yes, we can hear you.
Yeah, now share my screen.
And yeah, we can see the presentation.
Okay, great. So thanks a lot, James, for the introduction. So in my talk, I would like to discuss actually two things. So first, I would like to discuss this materials genes concept and tell you a little bit about what it means and why do we need this in material science. And then I would like to move on to a second part where I'm going to discuss how we can extract uncertainty estimates from SISSO models, which allow us to use SISSO in an active learning context or sequential learning context. So that's the second part of the presentation. Okay, so in my group, we are working with AI concepts and methods and applying them to material science with a specific focus in heterogeneous catalysis. So I'm going to start this presentation by motivating this need for this concept using this catalysis concept. So why do we look at this materials function? Because, well, the catalytic performance is an example of a materials function that is governed by an intricate interplay of many processes. So what does this mean? Well, in principle, a catalyst is a material that is able to convert a certain reactant molecule to certain products of interest, no? And we want to do this efficiently and selectively. So we want to form only certain products, but not other ones. And the catalyst does this by interacting with these reactants and products and intermediate using via its surface. So there's a lot of discussion on surface reactions that take place that form and break bonds on the surface of these materials in order to form these products. So that's a lot of different proposals and methods to study these surface reactions. However, this is not the only process that is taking place when we talk about heterogeneous catalysis. We have a series of other underlying processes that might also be very crucial for the reactivity of a catalyst or for its performance. So some of the examples of these are the restructuring of the materials under the reaction conditions. So actually the material, which is normally a solid, will respond to the environment of the reaction and may restructure, especially on the surface, forming different types of motifs that were not present beforehand. So this makes it really complicated to address. And we also have other processes such as sintering, where different catalyst particles, they come together to agglomerate and form bigger particles, or transport that is happening at different time and length scales. And the problem is that also that these different processes, they are not independent. So there is an interplay of all these processes, and this is very intricate, meaning that what happens in terms of the restructuring of the materials will also impact the surface reactions. And also the type of molecules that we form during the surface reactions will also affect the transport. So this makes the situation really complicated. So what have we done in terms of the material science community to address these questions or to model catalysis? So one way of doing that is using atomistic simulations, where we start with the description of this surface reactions. So basically, we go to this very small time and length scale, and we do a very detailed analysis, for instance, by means of electronic structure calculations or so, or similar. And then we build up on this multi-scale modeling to reach these other processes that are happening in much higher time and length scales. However, I think it's safe to say that modeling explicitly all these processes at the same time, it's unfeasible, and it's maybe not the best idea, because there is so much intricacy that the atomistic simulation will struggle to find this all these different processes. So that's the reason why we were thinking about a different approach to address this problem. And what we have been doing in my group in the last few years is to actually move to this materials genes concept. So here, the idea is to identify correlations or rules that by using artificial intelligence. So we want to identify correlations describing materials in consistent data with artificial intelligence. So let me guide you through the process, so the steps of this approach. So this approach starts with systematic experiments, which are going to synthesize the materials, characterize them, and test the performance under realistic conditions. And here I would like to mention that it's very important from our experience that these experiments are done systematically and consistently, so that we have good data or consistent data generated. Then in a second step, we might add some atomistic simulations where we are going to look at materials properties that we can calculate using different methods, for instance, density functional theory. And here, especially in the case of catalysis, we can also include environmental effects or model environmental effects that can be sometimes hard to be measured experimentally. And here I would like to highlight that these atomistic simulations often look at model systems, not really realistic systems. But this is not a problem, because we're going to combine the information of experiments and simulations in this approach. So once we have done all these experiments and the simulations, we now have a consistent data set that will have a target of interest, which is our measure performance. So we can think about this as, in the case of catalysis, as an activity or selectivity, but you can imagine also a different type of materials property, for instance, a band gap or a formation energy. And then we have, and on the other side, candidate discrete parameters, which I will call primary features in the context of SISSO, that are going to be properties or physical parameters that were measured or calculated. So measured by these experiments here, these characterization experiments, or calculated by the simulations, and they will reflect many possible underlying processes. And here I would like to highlight that initially, when we start the analysis, we might not know which are the important processes. So we offer many of these parameters that correlate with different underlying processes. And then, well, then we are ready to apply AI. And here the idea is going to be to apply SISSO to map this performance as a function of key parameters out of all of these initially offered candidate parameters. So the idea here is that we are going to use the algorithm for finding the right representation. So we want to have a function, in the case of SISSO, as discussed by Tom, this is going to be an analytical expression, but we want this function to depend only on few parameters, not all the parameters that we offer initially. And in analogy to genes in biology, we call these key parameters as materials genes of a certain property or function. And why do we use this analogy? Well, just like genes in biology, these materials genes, they will not provide the comprehensive understanding of the underlying processes that bring the parameter to the property, but they will capture complex correlations that we cannot maybe do it without the aid of artificial intelligence. And second reason why we use this analogy is that the description that given by the materials genes will be statistical. So it's not going to be something that will, so the description will be associated to an uncertainty, so some variance that we are going to, I will come back to this point later. Okay, so this is the idea here and the materials genes concept. So this is similar to what we have, for instance, how a gene determines the color of our hair or our the likelihood that we have cancer. For instance, this is the idea here. And in other words, in the context of SISSO, we are going to be looking at these descriptors that we had in the previous presentation. So these D1 and D2 here, which are functions that will map the performance of the different materials. So we are trying to find coordinates of such maps of materials that will allow us to arrange the materials according to their performance. And here, so I highlight that only few parameters will be in the coordinates of these maps. And if we are successful in this analysis, what we can get? Well, first we are going to have predictions, so we can try to understand what we should modify in an existing material to get a better performance, or even trying to find a completely different material, because we know the regions of this material space where our search has to be focused. And we are going to also have physical insights, because we have identified the few key parameters out of many offered ones, so we can discuss how they relate to the underlying processes. So this is the idea here. We got insights and predictions using these materials genes, and for this we're going to be using this interpretable AI approach, SISSO. Okay, so let me give you an example of how this can work, and I'm going to discuss this example where we have. Just let me hide this. Okay, just 1 second. Yeah. So I'm going to discuss like this example where we are going to be identifying materials genes using SISSO, and these are this is an example in a catalysis where we have silica-supported cobalt nanoparticles applied in the reaction that is CO2 hydrogenation. So here, the goal of the reaction is to form methanol, which is one of the value-added products for CO2 hydrogenation. So the reason why our experimental collaborators were looking at these systems, in addition to our concern about the global warming, is the fact that this system, so this cobalt nanoparticles supported on silica modified with different additives, they mimic the environment of hydrothermal vents, which are fissures on the seafloor that discharge heated water. And these systems are interesting because it is believed that the first organic molecules on the planet were formed could have been formed in these systems via catalytic hydrogenation of CO2. So that's why we want to investigate these systems. So these are cobalt nanoparticles that are supported on this amorphous SBA15, so it's a silica oxide support. And in this support, we have different metals, this M here, that are going to be introduced during the synthesis method. And what is interesting here is that depending on the type of M, so depending on the type of additive that we add in this in the system, we have a different formation of different products. So here I show you the selectivity towards 3 different products. And you can see here that these different colors, we have different profiles according to the method that we have there. And so this is a reaction that is taking place at a relatively high pressure and significant temperature. So what are the questions here we want to address? Well, we want to understand a bit better what is the role of the support and why do we have this change in reactivity as we introduce different additives in the support. And also we would like to find a way to design a new support, maybe to discover like a new catalyst material for CO2 conversion. Okay, so how we created the data set here. So this is an experimental theoretical data set, so including these 2 components, the experimental component and the theoretical component. And so this data set has in one hand our target, so our measure performance, which is going to be the methanol selectivity. So this is our product of interest. So this selectivity quantifies how much of these products were converted actually to methanol. So we have production of methanol, but we also have CO and methane, which are undesirable. So we look at how much methanol was produced. This is the methanol selectivity. And this comes directly from experiment. Then we also have 33 candidate descriptive parameters that come from experiment also. So we have a range of different techniques that were utilized to characterize these materials. And now we have also theoretical parameters that will come from simulations on a model system. And here I say a few words about these simulations. So these are simulations done using DFT RPBE with the FHAIMS code. So they are, for instance, properties of adsorbed molecules, for instance, CO2 or different intermediates that can be formed during this reaction. So for instance, methoxy or COOH or carbon monoxide and so on. And there are also properties that tell something about the charge of CO2 adsorbed on these interfaces and the charge on this additive metal that is in the support. So here I would like to highlight 2 things. So first, this is a very simplified system compared to the real one. So we have a cobalt-20 cluster. But we are able, with this very simple system, to model something about the interface effects between the cluster and the oxide support in the presence of this additive. And second thing, I would like to refer to this webinar from Rei Miyazaki that has discussed in details this type of system. So if you're interested, there is a webinar in Catalysis that already took place, so you can find the recordings online. So there you have more details on how this was done. Okay, so now I told you we have experimental candidate parameters, theoretical chemical parameters, and then we also have elemental chemical parameters here. And these are coming from experiment, a calculation, and they are very simple properties of the elements that were introduced in the support, for instance, the covalent radii or something like this. Okay, very good. So now I would like just to quickly recap about SISSO. So this was nicely explained by Tom in the previous presentation. So this is a method that has this, maybe we can say 3 steps. So first we have to choose the input parameters, which we call primary features. So we use our knowledge about the system and possible underlying processes to choose these primary features. So it's important that we don't miss any primary feature that can be relevant. Then we have this feature construction step where we combine these primary features by applying unary and binary mathematical operators. So we form more and more complex expressions. And here we form what I will call candidate feature space. And then we apply the complex sensing methodology to select the few of these candidate features that will be combined by weighting coefficients to form the final model. So this is done by looking at correlations between features and the property for the data set. And also we look at correlations between the residuals of the previously identified models and the expressions that we formed during the SISSO analysis. So after an L0 minimization, which is the so-called Sparsifying operator, we form this type of model where we have these DIs here, which are the analytical expressions that are the components of the descriptor, and CIs that are the fitted coefficients. Okay, so here, so these DIs are the descriptor vector, and the model is actually obtained by simply multiplying these analytical expressions or the descriptor components by some constants that are fitted. Okay, very good. So by using these descriptors, we can form these materials property maps that I showed you in the beginning. So here, D1 and D2. For instance, so this gives us like also a nice visualization of this material space and an overview. And one thing I would like to highlight here is that we are choosing like a very low dimensional descriptor. So the number of analytical expressions that we have in the final model is very low, for instance, 2 or 3, compared to the number of candidate features that this algorithm will screen. That is in the order of billions or even trillions of candidates. So meaning that we are really having a very comprehensive or very big library of different expressions, and we are selecting only very few ones in the final model. No? Okay, very good. So now going back to the application now, I will discuss now the performance of the SISSO models that were for methanol selectivity that were derived using different types of features. Here, I would like to show you this absolute prediction error. So these violins, they correspond to the different types of errors that we have. So the width of this violin corresponds to the number of systems that have a certain absolute prediction error in the y-axis. And here, what we see from this, and this box plots show some statistics of this error distribution. So what we see from these violins here is that we have a better description when we combine theoretical, experimental, and elemental features compared to the case where we only use one type of candidate descriptive parameters or primary features. So meaning that we have a synergy between the description that we can obtain with experimental information and theoretical. Yeah, so we need both of them to achieve like an accurate model. So this is what is shown here in this violin here, that is the one corresponding to this model. Okay, now we can look at the expression of this model. So the analytical expression of the model obtained with these features here. So this is what is shown here. And we can discuss what are the parameters that enter there and what is their physical or chemical meaning. So here we have, for instance, the CO2 conversion. That is one experimental parameter that was offered in the analysis. So obviously the selectivity depends on the conversion of the CO2 molecule. Then we have a parameter that comes from experiment. This is the temperature of the first hydrogen temperature program reduction signal. So this parameter tells us something about the reducibility of the material. So the lowest is this, the lower is this temperature, the more reducible is the material. So meaning that as the reducibility of the material that is changing as a function of the metal additive is important for the selectivity towards methanol. Then we have a parameter that comes from theory. This is the formation energy of this methox intermediate. So this is this species that is shown here. So this means that this species might play an important role in the chemical reaction, especially in the reaction network. So it can maybe be an intermediate towards the methanol, or maybe it's blocking or poisoning certain sites. So this is meaning that this is there is a role for this intermediate. And finally, we also have the covalent atomic radius of this M species. That is also an important parameter, an elemental parameter that does that the size of this metal additive that we introduce in support is important for the reactivity. So this is the type of analysis we can do by using these materials genes that were identified by SISSO in this model. So yeah, that's what I wanted to illustrate here. Okay, now can we use some SISSO model to discover new additives or new supports? And that's what we did next. Actually, we trained a different model by only using elemental parameters. That is a very simple parameters that only tell us something about the chemical composition of the material or the support. So we fix the cobalt nanoparticle. We only change the support. And by using this model, which is not as accurate as the previously identified one, but still has a decent accuracy, we can screen different types of additive elements that we can introduce in this support. So here you see the results for many different possible additive metals that are introduced. So these are only SISSO predictions. So we have selected two of them. For instance, this material based on vanadium and zinc. And we have looked here at the predicted values. So this is the prediction of the SISSO model. And we also evaluated here, we estimated the uncertainty of the prediction by using the standard deviation of these predictions that were obtained during cross-validation. So this was one material out, leave one material out cross-validation. And here we see that, well, this prediction is, so this material should be quite good, quite high selectivity and with low uncertainty. So this is a good candidate. And for
Progress.
used it to estimate the property for this huge material space. So that's what we are normally doing. What is the problem of this approach? So there is, there are several problems, but important for this presentation is that the model performance is typically assessed in average. Yeah. So when I show you this distribution of errors, these violin plots, normally we don't even analyze the whole distribution of errors, but we use the mean value as an indication of the performance of the model. And well, this might be fine in some cases, but often what we see is that a good performance in average might not translate to a good description of promising materials, simply because the data set that we are using to train our models might not be representative of the material space where we want to cover, for instance, high performance materials. Okay, so this is an issue because this will hurt materials discovery. So realizing this issue, well, the community has been shifting from this prediction type of approach to the action type of approach. What do I mean? So the idea here is actually not using the AI model not only to get a prediction, but also to inform our actions. So this is what we call AI-guided workflows for the discovery of materials with optimal properties. And I will discuss how this works in the context of black box optimization of materials properties, which is an approach where we have the iterative modeling and data acquisition, the processes to identify materials with desired properties. So for instance, high values of a certain properties or a value in a certain range. So how does this approach work? Well, now we again have this material space. We have this few known properties. So this black here, so are the labels. And we again train the AI model to get like an approximation of this property. But now we are going to use the information on this AI model, especially predictions and uncertainty estimates, in order to inform what we call an acquisition function that will help us deciding which are the next materials for which we have to evaluate the property. So what we should where we should obtain this property by using an experiment or a calculation. And then once we have chosen this, we add these materials to the data set, and then we restart this process and adding more and more data. So here the idea is that we are going to do this iteratively, and we hope to reach some maximum or to identify very fast materials with desired properties, for instance, high values. So you see here from this scheme that it's going to be crucial now, not the predictive capacity of the model, but also the uncertainty estimate, because we are going to have the two components entering this acquisition function. So we have a crucial role of this acquisition function. And the reason why we use predictions and uncertainty is that we want to actually exploit the model. So to use the model to indicate which are the materials that are the most promising, but we also want to explore the material space in regions where the model is not sure about the prediction. So that's why we need the uncertainty estimate. Okay, so I will discuss now how we do this in the context of SISSO. So an AI-guided workflow based on SISSO. Can we do this? Okay, so this is the example that I would like to discuss. So this is a materials discovery workflow that will identify acid-stable oxides for the water splitting reaction. So in particular, we are going to screen and try to find binary and ternary oxides that are stable under oxygen evolution reaction conditions. So our target property here is going to be this decomposition energy at these reaction conditions. So this is an important problem because many of the oxides that are promising materials for this reaction, they will not survive under the conditions of the reaction. For instance, that could be very low pH and very high applied potentials. So this is the type of our target. So this delta G here is indicating whether a material is stable or not under these conditions. And this is done using a Pourbet diagram analysis, which actually is a phase diagram that tells us which are the phases that can be stable at certain pH or applied potential conditions. So here we are looking at oxides. So many of them are not well described by standard DFT approaches, such as based on GGA approximation. And here, for this reason, we are using DFT HSE 06 calculations that were also performed with the FHM's code, so very accurate calculations. And well, we have a recent efficient implementation of these hybrid functionals in the FHM's code that allows us to do this very efficiently. Okay, so now our initial data set is going to be 250 materials, so oxides, mostly binary. And our material space is going to be a space of more than 1,000 materials. And here are mostly ternary oxides. And I would like to also mention that the calculation of this property here involves, for one oxide, involves the evaluation of many different materials that are competing phases of this oxide. So metallics or intermetallic materials, hydrides, and so on. So this means that in order to get the property value for one material, we actually need to calculate many more, maybe even 20 or 30 materials. So this is why we need to intelligently select with AI, which are the oxides that are the most promising.
Lucas,
Okay.
just to say, you have just under 5 minutes left.
Yeah, okay, good. So we are using primary features that are 14 physical descriptive parameters that depend on the composition, atomic radii, and oxidation states, and the SISSO approach. So this is the type of map we obtain when we use the training set. So here we identify these two coordinates that allow us to map this delta G pur B. And you see here they depend on different parameters. And we have a nonlinear operation that are entering here. So these are properties, for instance, the standard deviation of oxidation states, the radii of certain elements, and so on. So these are very simple compositional properties. Okay, so now if we want to use this iterative loop and an acquisition function that will have in this probability of feasibility acquisition function that will measure the likelihood that the target value is lower than a certain threshold, we need to obtain predictions and uncertainty estimates of these SISSO models, which is not we don't get from this SISSO map here. So what we have done to address this is to create ensembles of SISSO models, and we use 3 different strategies for that. So the first one is what we call standard bagging, where we are going to first bootstrap the data set. So by sampling with replacement from this data set to create different data sets that have slightly different materials in the data set. And then we are going to train different models with each of these slightly different data sets here. So we have not only one model, but several models and several predictions. And finally, we have this aggregating step where we are going to look at the prediction of the model is going to be the mean of all of the predictions for the different models. And most importantly, we can use the standard deviation of these values, of these predictions, to get an estimate of the uncertainty. So this sigma here is going to be our uncertainty quantification. Yeah. So this is the first standard bagging approach. We also try different approaches that are based on this bagging, which are, for instance, training models with different complexities. So we still do the bootstrap process here, but we train different models with slightly different complexities compared to the optimal one that we identified using cross-validation, for instance, models with higher and lower dimensionality. And finally, we have this third approach where we do Monte Carlo dropout of primary features. So here, in addition to performing this bootstrap procedure to obtain different training sets with different materials, we have also dropped a fraction of the primary features that are used to train different models. And here we again obtain different models with slightly different features. So here we have variability in the material side, but also in the feature side. And we again can evaluate predictions and uncertainty estimates using the aggregating step. Okay, so I'm running a bit out of time here, but I would like to tell you like how we assess the quality of these uncertainty estimates. And we are using these different metrics. One of them is this miscalibration score, where we look at the ratio between the error, absolute error, and the standard deviation of this ensemble. So our uncertainty estimate. And we look at the distribution of these Z values, which are unitless, for the different models or the different types of ensembles. So if this value is close to 1, we have a well-calibrated model. If this value is higher than 1, we have an overconfident model. And if we have this value between 0 and 1, we have an underconfident model. So this is the result we get with the bagging approach. So we see that this is like a very overconfident. So these Z values are very high, which we actually mitigate. So this overconfidence problem is mitigated by using this bagging, for instance, with different model complexities or with different primary feature dropout. So this is what we get here. So this is a bit inspired in this random forest approach where we don't use all of the features to train the model. So this seems to mitigate this overconfidence issue in the case of the SISSO ensembles. Okay, so now we have all the ingredients now for this optimization. We have the acquisition function, we have the ensemble of SISSO models with uncertainties and predictions, and we are using here the primary feature dropout procedure. Okay, so now we can run this approach, and we look, for instance, at the results in terms of the number of acid stable discovered materials as a function of the number of iterations that we run this. And we see that by using this workflow, we discovered 12 materials that are stable oxides according to the DFT HSE calculation in 30 iterations only. So this means that the chance of finding a material by using this workflow is much higher than the chance of finding it using random sampling. Actually, if we randomly select these materials in this material space, we see that we barely find like stable materials, only 2 in 30 iterations. So this shows that this is an efficient approach to choose actually which are the materials for which we perform the calculation. We can also visualize these results using this map. So this is the map I showed you before. So the region of interest is the region of low delta G per B. So this indicated in red here. So this is the initial training set. So these black points. Now I show you the candidate material space. So we see that not many of them will fall in the region of interest. So only few points are here. And here are the materials suggested by random sampling. So if we randomly select, so this is our baseline, if we randomly select materials from this space, they're mostly falling in the unstable region. Yeah, that's why here we need this type of approach to choose which are the materials that we need to investigate. Here, one thing that is also clear from this map is that many of the materials that we discovered, they were already predicted to be stable from the initial map. So we would not need to add more data to get these materials correctly. However, we also see that some materials that were not correctly predicted as stable from the initial model, they were discovered by this sequential learning approach because the prediction improved during these loops. No? So we not only find the materials with good performance, but we also have an exploration component that allow us to improve the description of the material space for regions of interest or nearby. Okay, so let me just conclude with these 3 statements. So I showed you how a consistent, so we can use consistent data, especially using experimental data and theoretical data along with SISSO for identifying these materials genes that are the key parameters that correlate to the process that trigger, hinder, or favor some kind of materials property or function. I showed you also how different ensemble approaches can be used to obtain uncertainty estimates of SISSO predictions. And in particular, this approach combining bootstrap and primary feature dropout seems to be a reasonable approach for the future. And as an outlook, I would like to say that we would like to improve these SISSO guided workflows in 2 different directions. So first, with a more informative data set. So how do we start the active learning, or what is the first step? So how to choose this data and how to get data with a lot of information that helps us modeling the materials property. And also, I mean, there we still observe some overconfident issues with our uncertainty estimate. So we should also be looking at more reliable uncertainty quantification so that we improve the efficiency of such workflows. With that, I would like to thank you a lot for your attention. And these are also the people that are involved in all of this work. So Matthias Schäffler for his support during several years. Ray Miyazaki, which was postdoc with us here, working on these Cobalt systems, the integration of the theoretical and experimental data. Akil Nair, which is the person behind this ensemble approach and the active learning that I showed in the end of the presentation. And our experimental collaborators, Kendra and Harun Tuisus, from the Max Planck Institute of Forschung here in Germany. Thanks a lot, and I'll be happy to get your questions.
Okay, thank you very much for this nice talk, Lucas. And yeah, the floor is now open for questions. So again, people on Zoom, you can type your questions in the Q&A button at the bottom, or raise your hand and I can unmute you. And yeah, for people on YouTube and Kushare, you can write your questions in the chat there. And we do already have a question on YouTube from Lapawat. So they say, thank you for the very nice presentation. Is there any rule of thumb to get a set of descriptors for a target we're interested in? For example, absorption energy of an intermediate on a different surface.
Well, what I think we often get this question, and my answer would be we should not forget anything that we know that might be correlated with this property. For instance, if you think about absorption energies, we know that the D-band center, for instance, if you have a metal surface, is a good descriptor for that. So this is one of the descriptors that should be there in the analysis. However, we should also offer descriptors that we initially are not sure about the relevance of, because we might be surprised at the end of the analysis to find correlations that we didn't really think of. It's difficult to say that if we have a rule of thumb, but I think the important thing here is that we do not miss what we know or that what we suspect to be relevant.
Yeah, because the whole concept or one of the main features of SISSO and this materials genes concept is you're kind of using physical information to get the properties that you want, right? So yeah, using things that you already know is helpful, but yeah, having
Yeah,
additional
they
things
should be
that you...
definitely have a physical meaning, right? We don't
Mhm.
offer things that will not have a physical meaning. But yeah, this is the idea.
Mhm. Okay, so yeah, hopefully that answers your question. And don't see any other questions right now. Maybe I could just ask a quick one on the first part of your presentation. So why did you choose these two particular materials to synthesize? So why not one with a higher catalytic activity or...
Okay, it's a good question. So we looked at the materials for which we had the synthesis reported in literature, and we chose the ones we knew how to make, because developing the synthesis of a new material, especially those complex materials where you have a metallic particle supported on an oxide, might be challenging. Yeah. So then we just, the reason for the choice of these two materials is we had a good synthesis recipe. And I think this is one of the big challenges in materials discovery, right? To get these synthesis recipes or calculate exactly how these materials can be synthesized.
Yeah, because models can predict super good catalytic activity or whatever, but if it's impossible to synthesize or uses some very rare elements, then it's not so useful at the end of the
Yes,
day.
definitely, yeah.
Yeah, not seeing any other questions right now, but I'll just give a couple more minutes for anybody to type one out. Or to, yeah, again, you can raise your hand if you prefer to speak the question. Again, while people are thinking, I can also say at this stage that the hands-on session tomorrow will kind of demonstrate how, or will show some of these materials maps and how the SISSO method works in combination with this active learning approach that Lucas showed in the second part of the talk. And yes, hopefully many of you have already signed up, and we'll see you there, and you can kind of follow this procedure in a very intuitive way with just a hands-on point and click GUI to do this. Maybe I can also ask, is the SISSO model you used in these applications, is this with the improvements that Tom described in his talk, or is it using an older version of SISSO, do you know?
This is using the SISSO++ code from Tom, so everything
Okay.
is there. We didn't include the parameterization actually for these applications, but it's in recent works we use the parameterization, also of some operators, and we see that this is quite beneficial in some cases.
And it also uses this unitless or unit preserving property.
Yes,
Yeah.
yeah. I
Okay.
think the unit thing, there's no reason not to utilize that. Now for the parameterization, this includes means more cost of the calculation, because the nonlinear optimization will be costly depending how much we parameterize, as Tom explained. So I think we should be probably more selective when we are restricted from the computational perspective.
Okay, so we have one question in the chat. So say thank you for the nice talk. I'm thinking, what if we miss out some primary features in the SISSO approach?
Yes, this will happen, especially when we don't know exactly what's happening in our materials function. What I can say is that from our experience, we see that SISSO tries to reconstruct information of an important feature that is missed based on other features. So we should also mention that in the analysis, we typically offer features that might be correlated and that might be related to each other. So this is the typical case. And we see that there is this reconstruction of information. But now if we miss something that is crucial, whose information, if we miss a feature that is crucial, whose information cannot be reconstructed by the other features, then I think this is going to be a problem. Good news is that there are ways of assessing that, especially when we look at prediction errors and cross-validation schemes. We might have like an idea of if we missed the important features or not. But I think in general, it's difficult to tell if we missed something that was not offered.
Yeah. So how many kind of different choices of features do you usually try out?
So as mentioned by Tom in his talk, so if we offer too many features and if we go to too high rungs, we have the complexity problem, right? We are going to have, it's an NP hard optimization problem. So we need to carefully select, but I think it's safe to say that we can handle like 20 to 30 features, at least at lower rungs, if we look at rung 1 and 2 models. This is already enough for many applications, I would say.
Okay, thank you.
I mean, can I just add? I mean, if you really miss a very critical feature, you will not get a good fit, right? So if your SISSO description is not good, that actually tells you missed something, and you have to go back to the primary features. So you get immediately, I would say, a warning that something is wrong if your prediction error is too big.
Matthias. Okay, so I think I don't see any other open questions at the moment. I think Lucas, you're here tomorrow in the morning.
Yes, yeah,
right?
I'll be there for the hands-on. So any other questions, you can feel free to ask there, or just email me. It's also nice.
Yeah, okay. Then yeah, thank you again to Lucas for the talk and answering the questions, and thank you also to Tom for being here and for his talk as well. So yeah, I think I will close this session now, and yeah, just remind you all that there is the hands-on session tomorrow. You can still sign up if you haven't already.
Recording stopped.
And yeah, hope to see many of you there and also in future FHIM's webinars that we run as well. So yeah, thank you everyone for being here.
Bye, thank you.
See you soon.